My third elemental love is hydrogen. In this case, my passion was only kindled 6 years ago. But the story of hydrogen in the world of zero emissions energy goes much further back than that. Have you heard of the legendary French novelist named Jules Verne? He wrote the classics such as 20,000 Leagues Under the Sea, Around the World in 80 Days, and Journey to the Centre of the Earth. In another of his books called The Mysterious Island, that was written in 1874, that's nearly 150 years ago, one of his characters said the following, and I'm going to quote a passage here. Quote, "Yes, my friends, I believe that water will one day be employed as fuel, that hydrogen and oxygen which constitute it, used singly or together, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable. Someday the coal rooms of steamers and the tenders of locomotives will, instead of coal, be stored with these two condensed gases, which will burn in the furnaces with enormous calorific power. When the deposits of coal are exhausted, we shall heat and warm ourselves with water. Water will be the coal of the future." Just beautiful.
How prophetic.
So, what does the science tell us about hydrogen? It is the first element in the periodic table. It has one proton and one electron. No stable element could be simpler. Hydrogen is the origin of all things, literally. It and helium were the first elements to form from the sea of protons and electrons created in the Big Bang. But there was much more hydrogen than helium. And in the furious nuclear fire inside stars and supernovae, hydrogen nuclei fused to form helium, and ultimately, with successive rounds of fusion, every element in the universe. And now, even today, after 13.7 billion years of fueling the stars and the supernovae, hydrogen accounts for 90% of all the atoms in the universe.
Fascinating.
Yeah.
Here is another statistic, amazing. 2/3 of all the atoms in our bodies are hydrogen. If silicon is the king of microprocessors and lithium is the queen of batteries, then hydrogen is the creator of all things. Hydrogen is important in the modern world for many reasons, but I want to tell you about its role in helping the world to achieve net zero. The biggest challenge of all is to replace oil, coal, and gas. Consuming these three fossil fuels accounts for nearly 3/4 of global greenhouse gas emissions.
Yes.
Stunning amount.
Yes.
And the way forward is simple. We have to replace the use of fossil fuels with electricity. Not just any electricity, but zero emissions electricity from solar panels, from wind turbines, from hydroelectric reservoirs, and from nuclear power plants. Electricity is like magic. It can be used to heat and cool our buildings, to run powerful motors for transport and industry, to provide lighting and to run our computers. But even magic has its limits. Sometimes we need higher density energy storage than can be provided by batteries, such as to power huge long distance freight trains and trucks. Sometimes we need a high density liquid fuel, such as for international passenger planes. And sometimes we need to replace fossil fuels that are used as chemicals, such as in steel making, or for making ammonia to be used in making fertilizers. And this is where hydrogen steps up to the plate. We will still start with electricity. Science has taught us that water is composed of hydrogen and oxygen, H2O. More than 200 years ago, scientists discovered that by passing electricity through water, they could crack it into hydrogen and oxygen in a process called electrolysis. Today, engineers have designed giant machines called electrolyzers that can produce hydrogen at massive scale, powered by zero emissions electricity. So let me quickly tell you 3 incredible uses of this so-called green hydrogen. The first use is in steel making, or more accurately, the first step in the process of steel making. The first step starts with iron ore, which is fundamentally iron oxide, or more commonly, rust. The iron oxide has to be reduced to the pure elemental iron, because the iron is the main ingredient of steel. To do this, you have to heat up the iron ore with high purity coal in a giant device called a blast furnace. Inside the furnace, the iron oxide melts, and then the carbon strips the oxygen atoms off the iron oxide, forming carbon dioxide, which goes off into the atmosphere and leaves behind the elemental iron. And this process accounts for nearly 8% of global carbon dioxide emissions, which is a huge percentage of the total from just one industry. It's extraordinary. It turns out that all of the coal can be replaced by using green hydrogen and zero emissions electricity. And in that case, the only byproduct is harmless water vapor. The process of using hydrogen instead of coal in steelmaking is only just getting started. There are a couple of pilot plants, one in Sweden and one in Austria, but there are not yet any full-scale plants, but some have started construction. It's early days. Optimizing this process and replacing the thousands of blast furnaces around the world will keep scientists, engineers, and companies busy for at least 30 years or 40 or 50 years. The second use I want to mention for green hydrogen is to replace natural gas, that's methane, that is currently used to make ammonia. Who cares? Why is ammonia important? Because ammonia is used to make nitrogenous fertilizer. The world uses huge quantities of ammonia for fertilizer, and without it, we could only feed about half of the current global population. By replacing the natural gas in the ammonia making process with green hydrogen, we will be able to knock off another 2% of global carbon dioxide emissions. And the third and last use I want to tell you about is the most exotic. Currently, more than 2% of global carbon dioxide emissions are from burning jet fuel for jet engines and turboprop engines. Yes. Those big aeroplanes that fly 300 passengers nearly 13,000 kilometres from Mumbai to New York will never fly on batteries, because the batteries would be much too heavy. You couldn't take off. They will not be fueled by hydrogen either, because hydrogen is less energy, significantly less energy dense than jet fuel. So the smart way to replace the 2% of carbon dioxide emissions from the long distance aviation industry is to replace fossil jet fuel with synthetic jet fuel. To make synthetic jet fuel, you need just 2 elements, carbon and hydrogen, nothing more. Why? Because jet fuel, which by the way is also known as kerosene, jet fuel is a simple molecule consisting of a string of carbon atoms, like a string of pearls, that are decorated with hydrogen atoms. It is known as a saturated hydrocarbon. Now, it turns out there are ways to use electricity to capture carbon dioxide from the atmosphere. And as I've already mentioned to you, we can use electricity to produce hydrogen. With even more electricity, the carbon from the carbon dioxide can be combined with the hydrogen to make an absolutely carbon neutral synthetic jet fuel. So, starting with nothing more than electricity, air and water, we will be able to make unlimited quantities of jet fuel and fly long distances without doing any harm to our atmosphere. This is truly magic. There's a problem. The problem is that today it's very, very expensive. Scientists and engineers will be working for years to optimise the process and scale it up to the point that clean synthetic jet fuel will be a price competitive replacement for fossil jet fuel. The hydrogen industry is still in its early phases, so it is appropriate to ask, what are the frontier research questions for hydrogen? On the production side, it is about efficiency and cost. The engineers now and into the future have to work with the scientists to understand how to make the electrolysis more efficient, and then design better electrolyzers that will be cheaper to make and more reliable to operate at that higher efficiency. Similarly, the fuel cells that are used inside the cars and the trucks and the trains to convert the hydrogen into the electricity that powers the electric motors in those trucks, trains and cars. Those fuel cells, they're only about 50% efficient. It's important for driving range and operating cost reasons to push that efficiency up towards the theoretical limit, which is around about 70 to 75%. Another huge challenge is storage. For some applications, such as long duration energy backup in the electricity grid, thousands of tons of hydrogen will need to be stored in one location, in many locations. And this can be done by absorbing the hydrogen into metal hydrides, by compressing it, or by liquefying it. But all of these are expensive, and none of them are particularly efficient. Improving storage is another challenge that will keep scientists and engineers busy for another 20 or 30 years.